I'm Stephen Maldonado. I'm an assistant professor at the University of Michigan in the Department of Chemistry. My group's research that we've been recognized for this award is involved or based on the idea of making semiconductor materials that are used in all sorts of technologies, computers, laptops, phones, but in a way that totally redesigns and rethinks the general methods. The way that semiconductors like silicon are normally made is with high temperature processes involving lots of waste products and rather, I would say, nasty chemistry that you would like to avoid. Our basic idea is to see if we can make the same thing but basically under benchtop conditions where our reactors are not molten lava at 2,000 degrees, but it's a beaker of water. We've kind of taken elements from different fields. I'm an electrochemist, so I think a lot about electrochemistry, but I borrowed a little bit about crystal making from another discipline and kind of put together a hybrid system that we think is kind of a new take. Takes the best of many worlds, but in a way that I think adds the greenness that was never possible before in the semiconductor industry. So the detail, to go a little bit into the gist of it, is our idea is to take liquid metals. So basically things that, metals that melt at low temperatures, like solders that you put together circuits, and use that as a medium to grow semiconductor crystals. And the way we introduce the material into those liquid metals is electrochemically. So you take this little liquid metal, you stick it in a beaker of water that's got, say, dissolved sand ideally, and our process would enable you to go from sand to silicon in one step. And ideally what we really are trying to show and demonstrate is not only can you make materials this way, but really think about growing devices this way. So you stick in your beaker a platform with liquid metals, you pull out a cell phone or a laptop or computer. That's sort of the dream that we're pushing. But we've demonstrated the concept, at least in practice, works. Can we perfect it? I don't know. We'll see, but that's the idea. So one next step is to demonstrate an actual technology. We've been actually a bit successful in terms of making batteries, battery components. And so we're partnering with some companies to try to develop technologies directly. Another next step is to show that you can make not just, say, silicon, but all sorts of different important semiconductors. And so really trying to push the material synthetic approach. Another next step is to try to make those same materials, but in as high quality as possible. And we are sort of trying to figure out what's the best materials we can make. But back of the envelope calculation, we're talking about a factor of at least 5 in terms of energy savings. That's not assuming any sort of tricks. But the better thing is that you're doing everything at low temperature, so all the peripheries you'd have to worry about with high temperature go away. And now you're talking about using solvents like water, which is infinitely better than all the other sorts of chemicals that you do in the normal process. So when you factor all of that in, the energy savings become much higher. So ultimately what you need to have is a finished process, and we're not at that stage, but the savings there are very tangible and very real.